All right, let's pull back the curtain on something we all kind of take for granted. Instagram.
Right.
Think about it. We scroll, we tap, we double tap, and it all just works, seamlessly, effortlessly. But have you ever stopped to consider the truly mind-boggling feats of engineering happening every single second, connecting hundreds of millions of people?
It's easy to forget what's underneath.
Exactly. So today, we're not just looking at the pretty pictures. We're taking a deep dive into the intricate system design behind Instagram, drawing from some really fascinating technical sources.
There's some great stuff out there.
Our mission is basically to uncover that hidden architecture, the gears and levers, turning a simple photo upload into this global thing.
It's a fantastic challenge, actually,
Mhm.
because designing something like Instagram forces you to face these fundamental computer science questions.
Like what specifically?
Like, how do you get extreme scale, incredible speed, and absolute reliability all at the same time?
Yeah, that sounds tough.
It is. When you're building a platform for billions of photos, videos, where every interaction needs to feel instant to, well, everyone, everywhere. Every single decision matters.
From storing a pixel to generating a feed.
Exactly. How you store a pixel, how you generate that personalized news feed, it all becomes this complex, multi-layered puzzle. It's really a masterclass in distributed systems.
Okay, so that brings us right to the core problem. If we were just sketching Instagram on a whiteboard, for the first time, what are the absolute must-haves?
The essentials.
Yeah, the non-negotiables. What's the stripped-down version we have to build?
Well, at its heart, the system needs to let users upload, view, and share photos. And videos, of course.
Upload, view, share. Got it.
Users also have to be able to follow each other. That's key.
Right, the social graph.
And crucially, the system needs to generate and display a news feed, showing the latest stuff from everyone you follow.
Okay, core function's clear, but what about how it works?
That's where the non-functional requirements come in. And these are tough. The system must be highly available, basically, always on.
Can't have it going down all the time.
Soup. And we need to generate that news feed within, say, 200 milliseconds. Super snappy.
200 milliseconds. Wow. Why so fast?
Because a slow feed kills engagement. Users just won't wait.
True.
And, maybe most important for trust, it has to be absolutely reliable. No lost photos or videos, ever. Even if something breaks.
So zero data loss.
Zero. Those aren't just nice-to-haves, they're like deal breakers.
200 milliseconds, zero data loss, 500 million users. I mean, that sounds like a monumental task.
It really is.
So, given those requirements, what are the first things a system designer thinks about? What kind of scale are we really talking about, especially with all that data?
Well, what's fascinating, and kind of counterintuitive maybe, is realizing just how read-heavy Instagram is.
Read-heavy, meaning more viewing than uploading.
Way more. Think about your own usage, right?
Yeah.
You scroll and look at lots of photos, but maybe only upload one or two.
Yeah, that's definitely true for me.
And this isn't just a casual observation. It fundamentally shapes the whole architecture.
How so?
It means you prioritize quick retrieval. You optimize for reads. So you might sacrifice some strict consistency for better availability and speed when people are viewing stuff.
Okay.
You cache aggressively. You push computations to the right path when someone uploads rather than the read path. It's a trade-off. Very different from, say, a banking app where consistency is everything.
Right. You can't have eventually consistent bank balances.
Exactly. So for Instagram, efficient storage management is also critical. Photos, and especially videos, are big files.
Huge.
And low latency is vital for that smooth, instant feel we expect.
So what are the actual numbers, like user scale, data scale?
The numbers get pretty wild. Let's assume around 500 million total users, maybe 1 million daily active users uploading content,
Okay.
and maybe 2 million new photos, perhaps 250,000 videos, uploaded every single day. Now, estimate photos at, say, 200 kbd after compression, videos maybe 5-10 millibit. You're easily looking at over a terabyte of new data daily.
A terabyte a day.
Yep. Project that out just 10 years. You're talking somewhere in the range of 3.5 to 5 petabytes of raw media storage.
Petabytes.
Petabytes. And that's before you even think about making backup copies or storing different video formats for different devices.
Wow. 5 petabytes. That number alone is enough to make a storage engineer's head spin.
It definitely changes the game.
So how does that kind of colossal data volume immediately impact your database choices? I mean, you can't use a traditional single database, right?
No way. Traditional monolithic databases just wouldn't cut it. Not even close.
So what is the foundational blueprint? How do you start organizing that much data?
At a high level, the blueprint involves distinct specialized services. You definitely separate things out.
Like what?
You'd have separate services for handling uploads versus handling views or downloads. Each needs different optimization.
Okay, uploads and downloads are different beasts.
Totally. And each of these services is supported by its own optimized storage. You'd have dedicated storage for the actual images and videos, and then a separate database system just for all the metadata.
Metadata being like who posted it, when, the caption.
Exactly. So visually, imagine the Instagram app on your phone talking through a load balancer.
To spread the traffic.
Right. That load balancer sends requests to a fleet of web servers. These servers are stateless, meaning they don't hold user data long-term, so you can easily add more as needed.
Okay, scalable web servers.
These web servers then talk to, say, an image and video service.
Yeah.
And that service talks to both the actual media storage, think big object storage like Amazon S3 or Google Cloud Storage, and your main metadata database.
So the metadata database holds all the info about the photos and users.
Precisely. You'd need specific database tables or schemas, a user table for user ID, name, email, profile info.
Yeah,
Then photo and video tables with their unique IDs. The user ID of the uploader, the media path, basically the pointer to where the actual file lives in that object storage location data, creation timestamp, captions, likes, etc.
Lots of info per photo.
Oh, yeah. And of course, a crucial user follow table to track who follows whom. Just mapping follower IDs to followee IDs.
So even just the metadata, not the photos themselves, that's still a lot.
It adds up incredibly fast. With 500 million users, billions of media items, billions of follow relationships over 10 years, you're still looking at maybe 3.7 terabytes just for the metadata. And that's before the petabytes of actual images and videos.
3.7 terabytes of just text and IDs. Wow. It really is a tiered approach then, isn't it? Each layer doing its specialized job.
Exactly. Specialization is key.
Okay, so it sounds like you're building this system with many distinct specialized parts. We touched on separating uploads and downloads. Why is that separation so absolutely crucial?
Right. Goes back to that efficiency point. Uploads are primarily write-heavy.
Meaning they're adding data to the system.
Yep. And they often involve larger data payloads, like a whole video file. Plus, they can take longer depending on the user's network. Maybe some processing needs to happen.
Okay.
Downloads or views are overwhelmingly read-heavy,
Mm.
and they need to be lightning fast.
Because that's the main user experience, scrolling the feed.
Precisely. Now, if you tried to handle both uploads and downloads with the same set of servers, what happens when there's a huge surge in uploads, say during a major event?
Uh-oh. The uploads would swamp the servers.
Exactly. They could easily overwhelm the resources and slow down everyone trying to just view their feeds. It creates bottlenecks.
So separating them is like having different lanes on a highway, trucks in one, cars in another.
That's a great analogy. You optimize each lane for its specific traffic type. An upload service optimized for writes, a download service optimized for reads.
Makes perfect sense. Now, what about when things inevitably go wrong? Because in a system this massive, things will break, right?
Oh, absolutely. Failure is not an if, it's a when. Components fail, networks hiccup, data centers can have issues.
So how do you guarantee that ironclad reliability and zero data loss you mentioned earlier? That seems like the hardest part.
It requires designing for failure from day one. The key is redundancy and fault tolerance.
Redundancy meaning multiple copies.
Multiple copies of everything critical.
Yeah.
For every photo and video file, you store several copies across different storage servers, maybe even in different physical locations, different data centers, or availability zones.
So if one server dies or even a whole building has a problem.
There are other copies available immediately. And for our metadata, we use robust database replication.
So the user table, the photo table, they're copied too.
Continuously, often in a primary-secondary setup. If the primary database server fails, an automatic failover mechanism kicks in, promoting a secondary server to become the new primary, usually within seconds.
So the system stays up and no data is lost.
That's the goal. It's all about anticipating failures and having automatic ways to recover without impacting the user or losing data. You don't react to failure, you design around it.
Designing for failure. I like that.
Yeah.
Okay, planning for failure is key. But even with specialized services and redundancy, all that metadata, 3.7 terabytes you said, putting that in one single database, even replicated, just feels impossible at that scale.
You're absolutely right. It is impossible.
So this is where sharding comes in. That's the term I hear a lot.
Exactly. Sharding is absolutely essential. It's the technique for distributing data across multiple physical database servers.
Okay, explain sharding. Like, how does it work?
Think of it like managing a massive, constantly growing library. You can't just keep adding bookshelves to one giant room forever. It becomes impossible to manage and find anything quickly.
Right, you'd need different rooms or sections.
Precisely.
Yeah.
Sharding is creating those sections for your data. You split your massive database into smaller, more manageable pieces, called shards, and spread them across many servers.
So how do you decide how to split the data? What goes in which shard?
That's the critical question. There are a couple of primary strategies, each with trade-offs.
Okay, what are they?
First, you could partition based on user ID.
Meaning all data for one user, their photos, followers, everything lives on one shard.
Exactly. The big advantage is, if you want to fetch all photos for a specific user to show on their profile page, you only need to query one shard. It's very efficient for user-centric views.
Sounds good. What's the downside?
The downside is hotspots. Imagine a celebrity user with millions of followers and thousands of photos.
Their shard gets hammered with traffic.
Totally. That one shard could become overloaded, slowing things down for that user and potentially others on the same server, while other shards might be relatively quiet, like the Stephen King section in our library being mobbed while poetry is empty.
Okay, so user ID partitioning can be uneven. What's the alternative?
The main alternative is partitioning based on photo ID or video ID.
So each photo or video just gets assigned to a shard based on its ID, regardless of who posted it.
Right. You typically use some function, like hashing the photo ID, to determine which shard it goes to. This generally distributes the individual media items and thus the load much more evenly across all the shards.
That sounds better for load balancing, but what's the catch?
The catch is retrieving all photos for a specific user, since their photos are now scattered across potentially all the shards.
You have to query every single shard to find them.
Potentially, yes, or maintain complex indexes. It makes fetching a user's complete profile feed much more complex and potentially slower. It's called a fan-out query problem within the database layer.
Trade-offs everywhere. So user ID is simple for user views, but risks hotspots. Photo ID spreads load better, but makes user views harder.
You got it. And this brings up another important point. How do you even generate those unique photo IDs or video IDs in the first place? Especially if you want them to help with distribution or sorting?
Yeah, you can't just use simple auto-incrementing numbers across all those shards, can you?
Not easily. A single auto-increment counter becomes a huge bottleneck. So you often need a specialized, highly scalable key generation service, sometimes called a KGS. Think of something similar to how URL shorteners create unique IDs, but at a massive scale.
A whole separate service just to make IDs?
Often, yes. Or very clever distributed algorithms. And thinking ahead, you design logical partitions that aren't tied directly to physical servers initially. This lets you add more physical servers later and move logical shards around easily as the system grows, without massive disruptions.
That library analogy really works. Sorting by author versus sorting by catalog number and dealing with the super popular authors?
Exactly.
Okay, now let's move to maybe the most visible part for the user, the news feed. This is where the magic happens, right? Showing us fresh content from everyone we follow seemingly instantly.
Absolutely. It's arguably the most critical part for user engagement.
So how is that generated so quickly, especially considering all this sharding we just talked about, where person A's photo is on shard 1, person B's is on shard 5, person C's is on shard 3. How do you pull that together fast?
Right. Generating the feed effectively and quickly is a huge challenge. It requires delivering the most relevant recent content ASAP. There are a few main approaches or models people consider.
Okay, like what?
Well, there's the pull model. This is the simplest, maybe. Your phone, the client app, just keeps asking the server, hey, anything new for me? Anything new?
Like refreshing manually but automated.
Sort of, yeah. It frequently pulls the server for updates. Simple to build, but if you follow thousands of people, the server has a lot of work to do every time you ask. It needs to potentially query many users across many shards, aggregate the results, sort them. It can be slow and puts a heavy load on the servers, especially with millions of users polling constantly.
Okay, so pull is simple, but maybe doesn't scale well for the server or for users following lots of people. What else?
Then there's the push model.
Server pushes updates to the phone.
Exactly. When you upload a new photo, the server proactively pushes that update, or at least a pointer to it, into the feeds of all your followers.
Ah, so my feed is kind of pre-built on the server.
Pretty much.
Yep.
When you open the app, retrieving your feed is super fast because it's already assembled or mostly assembled. Great for read performance.
Sounds ideal. What's the catch this time?
The catch is that fan-out problem we mentioned earlier, but at the application level. What happens when a user with, say, 10 million followers posts a photo?
Uh-oh. The server has to push that update to 10 million individual follower feed?
Bingo. It's a massive write amplification. A single upload triggers potentially millions of writes or updates across the system. It can create huge processing spikes and delays, like trying to deliver a flyer instantly to everyone in a giant city.
Okay, so push is fast for reading feeds, but can be a nightmare for popular users posting.
Precisely. So because neither pure pull nor pure push is perfect, what often happens is a hybrid model.
A mix of both. How does that work?
You might use the push approach for the majority of users, the ones with a moderate number of followers, say, up to a few thousand. The fan-out is manageable there.
Okay.
But for the celebrities, the users with millions of followers, you don't push to all their followers. Instead, you might use a pull model just for their followers, or generate the feed on demand when those followers log in, or maybe just push to their most active followers.
Clever. So you optimize based on the user's popularity?
Exactly. You apply different strategies where they make the most sense. And to make all this feed generation efficient, especially with sharding, the structure of those photo IDs and video IDs we talked about becomes really smart.
How so? You mentioned generating them earlier.
Right. Instead of just a random unique number, you might design the ID to embed useful information. For example, a 64-bit ID could include, say, 31 bits for the epoch time seconds since 1970.
Okay, a timestamp built right into the ID.
Yep. It gives you uniqueness over decades and a natural chronological order. Then you might use, say, 9 or 10 bits for an auto-incrementing sequence within that second or millisecond.
Why the sequence?
To handle bursts. This lets you generate unique IDs even if hundreds of photos are uploaded in the exact same second, ensuring uniqueness and order within that burst. The remaining bits could encode the shard ID or data center location.
Wow. Okay, so the ID itself tells you when it was created and helps ensure uniqueness. How does that help the feed?
That embedded timestamp is gold. It means you can often generate a chronologically sorted feed just by looking at the IDs without needing complex database sorting across billions of items. When fetching feed items, you can query shards for IDs within a specific time range, making the queries much more targeted and efficient. It's a powerful trick.
That structured photo ID is genius for the news feed. Okay, so we've got this incredibly robust distributed system. It handles massive scale. It deals with fan out. It uses clever IDs. But how do we take it from robust to truly instant for the end user? What are the final touches, the sort of secret sauce that ensures that real-time speed and responsiveness?
Yeah, making it feel instant is the last crucial piece. This is where caching and load balancing become absolutely indispensable.
Caching, storing copies of things closer or faster.
Exactly. For static content, the actual photo and video files, which don't change, we use content delivery networks, or CDNs heavily.
CDNs, those are the networks spread around the world, right?
Precisely. They're geographically distributed networks of proxy servers. They cache copies of your popular content, that sunset photo, in locations closer to the users requesting it. So if you're in London viewing a photo uploaded in New York.
You get it from a server near London instead of all the way from New York.
Exactly. It dramatically reduces latency, the time it takes for the data to travel, makes images load way faster.
Okay, so CDNs for the big media files. What about the smaller stuff, the metadata? User profiles, follower counts, feed snippets.
For that dynamic, frequently accessed metadata, we use in-memory cache systems, things like Memcache or Redis.
In memory, meaning stored in RAM.
Yep. These are basically pools of superfast RAM sitting right next to our application servers. Accessing data from RAM is orders of magnitude faster than going to the main database, even if the database is fast.
So you keep copies of popular metadata in this quick access RAM.
Absolutely. A common strategy is based on the 80-20 rule, the Pareto principle.
80% of the views come from 20% of the content.
Roughly, yeah. So you aggressively cache that popular 20%, the most viewed profiles, the recent feed items for active users. This can allow maybe 30% or even more of all read requests for metadata and media pointers to be served directly from the cache, avoiding database hits entirely. Huge speed boost.
Makes sense. Cache the popular stuff. What about load balancing? We mentioned it earlier.
Load balancers are the traffic cops at the front door. They intelligently distribute all the incoming user requests, uploads, feed views, likes, comments across your fleet of web servers and backend services.
Not just round robin sending requests one by one.
Oh, much smarter than that. They use sophisticated algorithms, constantly checking the health and current load of each server. They route traffic away from overloaded or failing servers, ensuring no single server becomes a bottleneck. And that response times stay consistently low and stable, even under heavy load.
So CDNs, in-memory caches, and smart load balancing working together.
That's the trifecta for speed and responsiveness at scale.
What an incredible journey.
Yeah.
Seriously, going into the hidden mechanics of an app we just casually use every single day.
It's pretty deep, isn't it?
It really is. It's truly a marvel how all these intricate pieces, the sharded databases, the specialized services, the CDNs, the caching layers have to work together perfectly just to make Instagram feel so simple and effortless.
Yeah,
It's clear there's way more beneath the surface than just, filters and likes.
absolutely. And this kind of deep dive really highlights how fundamental computer science concepts aren't just theoretical.
Right.
Things like database design, distributed systems, redundancy, caching strategies, load balancing, they're applied in really innovative ways here.
These aren't just textbook ideas.
Not at all. They're the actual bedrock for creating these massive, scalable, reliable systems that feel instantaneous and, honestly, have come to shape a big part of our digital lives. Every tap, every scroll, there's this silent orchestra of technology playing in the background.
A silent symphony. I like that. So, what does this all mean for you listening right now? Well, the next time you're scrolling through your Instagram feed, maybe pausing on that perfect sunset photo or a friend's latest adventure, just take a moment. Consider that silent symphony, the servers, the databases spread across the globe, the algorithms, the caches all working in perfect harmony, just so that photo, that moment, can appear on your screen in basically an instant.
Makes you appreciate it a bit more.
It really does, and makes you wonder, doesn't it? What other simple-seeming apps, these tools we use every day without a second thought, hide such a complex and, frankly, beautiful universe of engineering just beneath their surface?